Hello everyone, welcome to lesson 5 of our energy series. This one is a big one. It's the conservation of mechanical energy in this case. So remember that we've looked at 3 different types of energy. We have talked about gravitational potential. So actually I think we go potential, gravitational. We've talked about kinetic, and we've talked about spring energy. These are all considered mechanical because these are sort of macroscopic interactions, if you like. So today we're going to learn specifically how to set up a conservation of energy question. And we're going to talk about some of the nuances here just before we get into some examples. But basically, this is our bookkeeping. This is our money in, money out, keep track of the numbers kind of idea. We're saying that the total mechanical energy of a system, in other words, the total amount of gravitational potential, kinetic, and spring energy, must remain constant. That has to happen when we're dealing with what we call conservational forces, or in other words, internal forces. If we start talking about non-conservative forces, that would be external forces, then we do not consider the total mechanical energy to be conserved. And we would represent that with a nice little picture. So I might say an example of a conservative force would be the force of gravity. So I might have an object, and here's my force of gravity. And then if I draw my system like this, hopefully you can see that the size of this circle, that everything inside the circle has to be conserved, since this force of gravity is acting within the system. So whatever goes in has to be the same as whatever comes out. So I would talk about the sum of the energy initial being the sum of the energy final. And I would say yes, because that is a conservative force. Conversely, if I had an applied force, so if I had a ball like this on the ground and I applied a force this way, well, in this case, I might draw the system to be here. And now you can see that this force is leaving the circle, leaving the system. Therefore, I would have to say that the energy initial is not going to be equal to the energy final. Okay, there would be some work done on the system. Since this force is going to be applied over a distance, there would be work done, and therefore the energy would be different. So just be aware of that as we move through, and hopefully there's a couple of little examples where we can talk about that. And so we kind of have the same scenarios we had when we first talked about work. There's 2 different ways to write out our physics principle. One of them would be to write a sum of the energy statement, looking at the total mechanical energy. So this would be the sum of the total mechanical energy initial before some sort of event would then be equal to the total sum of the mechanical energy final after the event. And then you just have to go through, look at the scenario and figure out, well, what kind of energies are there? So if we were to look at this example here, the total initial energy before the event is 800 joules based on the height and the kinetic energy. So if you look at this ball, it's moving, it's got some kinetic energy, but it's also got some height above this reference point. So this ball is moving and it's got height. As it reaches this moment in time, we can record how much total mechanical energy it has. Then an event will happen. The event will be it keeps moving in this area here. It's going to go from point A to point B, and that is the event that we're interested in. During that event, it loses some elevation, which brings it down to our reference point to be 0. So the gravitational potential energy would be 0. And because of the fact that gravity will be doing work on this object throughout this distance, then there will have been some increase in the velocity, and that number is given here. So pay attention to the total numbers. They will remain the same, assuming that there's no friction, and there's no air resistance, etc. And so we would have the statement, gravitational potential energy initial plus kinetic energy initial is equal to the potential gravitational energy final and the kinetic energy final. Easy peasy. If there is a spring involved, well, you just add it in. Notice that there's this spring energy here, this spring energy initial, and then there'll be the spring energy final, and you just keep track of all those values. That's primarily what we're going to be using, I think, to analyze our systems, but just note that you can do this just as easily if you look at the delta energies, the change in the energies, because essentially that change in the energy will equal 0. So in this case, you've got the change in the potential plus the change in the kinetic. Well, if you add those together, there should be no change. There is no change. That is the statement that we've made. We've said that they are conservative forces. There is no work being done external to this event or the system, and therefore the total change has to be 0. If you rearrange this, you're going to get this statement here. It's essentially the same. These two things are giving us the same analyses. They're just done in a little bit of a different way. Okay, let's look at an example. Here we have a pendulum. It's got a length of 1.8 meters, and at the equilibrium position, it is traveling at 3.75 meters per second. We are asked to find its maximum height. So we would probably go ahead and just give ourselves this reference point. 0 height would be the equilibrium 0 reference point, and then we are trying to find this distance here. All right, so I've gone ahead and just labeled these two different positions, and this is giving me my kind of event. My event is that the pendulum is going to oscillate back and forth, and it's going to move between position A and position B. That's my event of interest. Of course, it will keep going back and forth. There'll probably be a position C over here. I'm just not interested in that. I'm only interested in position A and B. So I'm interested in the energy between these two moments in time. This is my system. This is my event. The forces involved here are gravitational. So that is a conservative force. I'm ignoring friction. So the coefficient of friction here is 0, so I don't have to worry about any air resistance or friction in any way. So this is going to be a conservation of energy. So I'm going to say that at position A, the total mechanical energy at position A is going to be the same as the sum of the total mechanical energy at B. That's my physics principle, and that means I can now go ahead and do a conservation of energy analysis. Okay, so what kinds of mechanical energy do I have? Well, I've got kinetic and I've got gravitational potential. Okay, but maybe I want to be a bit more clear as to what those mean, just to keep my labels precise. I've got kinetic energy at position A, okay, and I've got gravitational potential energy at position A. Those are okay, so I'm just being a bit more precise. Then at position B, I've got the same. I've got kinetic energy at B, and I've got gravitational potential energy at B. Now, what we need to do is have a little look here. This would be, at position A, that's where the ball is going to start from, and it's going to swing all the way up to that same height. So this is actually the maximum height. So at the maximum height, hopefully you can see that the velocity will be 0. It's not moving. And at its lowest height, its height is 0. So that means that my kinetic energy at position A is going to be 0. So I'm just going to cross that out, call that 0. And at position B, since I've defined my reference 0 height to be at position B, that means I have no gravitational potential energy at position B. So that leaves me with this statement, that is that I have the gravitational potential energy at A. Let's call this mass times gravity times height. That is equal to the kinetic energy at B, which is half mv squared. Now, the nice thing here is that the mass does not matter. The mass is going to cancel out. And now I can rearrange this equation and solve for that height. So the height is going to be 1/2 times the velocity, which is 3.75 meters per second squared, divided by gravity, which is 9.81 meters per second squared. Okay, that gives me a value. Value is 0.716, 0.716, decimal, decimal, decimal. That is in meters, and that would be, let's turn that into centimeters. I'm going to use 3 significant figures, so it's 7.17, so that would be 71.7 centimeters. That is the maximum height that the pendulum reaches. All right, roller coaster question. Here we have a cart of an unknown mass, and it's got some speed, so it's got some kinetic energy at position A. It also has some height above this reference line, so it's going to have some gravitational potential energy. It's going to roll down the hill. We have no friction. We're assuming no friction, therefore these are all conservative forces. It's going to roll down the hill. It gets to position B. Still got some height, probably got some more speed, and then it rolls up again to position C, at which point it's going to have speed as well and some extra height. So let's go ahead and do a little bit of analysis and see where we get to. All right, we are interested in, we need to know the speed at C. So let's just say we have position A, we have position B, we have position C. Actually, we have position D as well. Let's just go ahead and do all of it. So the total energy of the system has to be the same for all 4 locations, or all 4 positions within this motion. So the sum of the energy, sum of the mechanical energy at A is going to be equal to the sum of the mechanical energy at B, which is going to be equal to the sum of the mechanical energy at C, which is, you guessed it, sum of the mechanical energy at D. Okay, well, at position A, we have, let's go ahead and put it, we have kinetic energy, and we have gravitational potential energy. Okay, then at position B, well, position B we have the same, but I'm actually not interested in position B. I'm interested in, I think I know something about position A because I know the velocity and the height, and I want to know something about location C. I actually don't care about B or D. I could go ahead and put all those numbers in, but frankly that's a waste of time. I'm only interested in A and C, and since I think I know all the information about A, that's going to unlock this scenario. So let's just flesh out A for a second. This is going to be 1/2 mv, so the velocity at A, squared, plus mgh at A. Now, do I know those things? Well, I don't know the mass. That could be a problem. I do know the velocity, and I do know the height. So that's looking promising. If we keep going for position C also has some, well, let's put it up here. We also have kinetic energy at at C. We have kinetic energy at C, plus the gravitational potential energy at C. So that's going to be 1/2 mv at position C squared plus mgh at position C. And I know this. I know the position, or I know the height at position C. I know it's 5.9. What I don't know is C. So that's what I'm trying to, the velocity at C. I'm trying to find that. Now, you may notice that we have masses being multiplied through every part of our equation. So, good news. We can cancel all of them. All of the masses disappear since they are being multiplied from every term in this equation. And that leaves us with a situation where we can solve for the velocity at position C. So let's rearrange this. We're going to go 1/2 v A squared plus GH at A. And now we have to subtract the term over here, so that's going to be minus GH at C, which we know. Now this whole thing, let's put more brackets on here, this whole thing is going to be multiplied by 2 to cancel out the half. And then finally, we get to isolate the velocity of C by square rooting the whole thing. And that will give me the velocity at position C. And if you do all the little calculations, being careful with all the brackets and the square root functions, you should get 8.6 meters per second. Let's pause for a moment and see if that feels right. Well, it's going from 8.6 down to 5.9. That's nearly half. So it has this initial speed of 4.5, and then half of the gravitational potential energy is converted into speed. So I would definitely expect this to be going up, and sort of feels like that's about right. I would also encourage you to be a good physics student here and put all the units in. I just put some values, but I recommend keeping the units in, doing the unit conversions, unit cancellations, and checking that you get meters per second. So go ahead and do that. Make sure you've got the right units. Okay, last example. This one's involving a spring. So we have a little cart, 250-gram cart with some speed, and it is rolling down this hill with an unknown height that we're going to try and figure out. It rolls down and it hits this spring, and it compresses the spring entirely until which point it stops moving. So there's this moment at the end where, let's call this position B, let's call this position A. At position B, there is no velocity, okay, the speed is 0, and since we're going to define this to be 0 height, we're also going to say that the height is 0. So hopefully you can sort of already intuit that the total mechanical energy at position B is entirely spring energy. But let's go through and figure out all the details. So we're going to do a conservation of momentum between position A and position B. We're going to say that there are no external forces, or there are no non-conservation forces, so there's no friction, there's no applied forces. All of the forces involved come from force of gravity and the force of the restoring force of the spring. So we will say that the sum of the mechanical energy at position A is going to be equal to the sum of the mechanical energy at position B. That is my physics statement, and hopefully we're getting comfortable doing that. Now all we have to do is flesh it all out. We're going to say that at the top, at position A, there is some kinetic energy. There is also some potential gravitational energy at position A. And, well, there's no spring energy. We might as well put that on there, but cancel it out right away. Okay. At the bottom, there may be some kinetic energy at position B, there may be some potential gravitational energy at position B, and there will be some spring energy at position B. But as we've already mentioned over here, there is no height, so the gravitational potential energy can disappear, and there is no speed, so the kinetic energy can disappear. So we're left with this statement, which is 1/2 mv at position A squared plus mg height at position A is going to be equal to the spring energy at position B, which is 1/2 kx squared. And in the question, we'll just check as we go through. We know the mass, so let's just do a little check of what we know. We know the mass of the cart, we know the initial speed, we know the mass, we know gravity, we know the height at position A. We also know the spring constant, so we know K, and we know that maximum compression, so that's my X. All that is left to do, oh sorry, I said that we knew the height, which we do not. All that's left to do is rearrange this and solve for that height at position A. Okay, so as you rearrange the equation, you should get these values. Be careful to make sure that your compression of the spring distance is in meters, so you've got to convert that. And you'll also note that whenever you have a spring energy in the system, because the term is not being multiplied by the mass, yeah, you can't just go ahead and cancel the masses with these scenarios. So the mass has to stay in, and you should end up with a height here of 74.1 centimeters.